So today we are looking at something called escape velocity. And it is defined as the minimum velocity required for an object of any mass to be launched from the surface of a planet. So in our case it's Earth, to a point in infinity where the potential where the potential that we learned earlier is 0, such that the object does not return back to the planet. So basically what we're talking about is that escape velocity is the minimum speed velocity at which you throw something out of your gravitational field or the planet's gravitational field, and it is like it should be sufficient so it can overcome the potential well that we talked about and can keep on going. It should leave the whole gravitational field. So you just need to remember that. Now basically we can actually calculate it. It's not very hard to do. So you need to understand that when something is going from the surface of the planet to the very end, that's infinity, which means that the overall gravitational potential energy would increase. Alright, and that gravitational potential energy is coming from the change that we have provided it. What I mean by this is that let's say that we provide some initial kinetic energy which basically should be equal to the total gravitational potential energy which is required to leave. Since we know that kinetic energy is given by half m and v square, where I can just write escape here so that this is the velocity that we need, it should be equal to the mass times the change in gravitational potential that we require, the change between infinity and the surface. So what happens is that the mass and the mass is going to cancel out, which will leave us only with the escape velocity whole square divided by 2, right? So let's just put it so you guys don't get confused. So let's put it here, and the change in potential. Now what I can do is I can write the change in potential like I can say the potential change can be found if I subtract whatever the potential is at infinity minus the potential at the surface of the planet. Right. Now if I write it this way, then let's further simplify it a bit. So the escape velocity then has to be, this is basically when you have something which is at a distance of infinity, so that value becomes 0. So it's going to be 0 minus, and here the surface, at surface the potential should be minus gm upon the radius of the planet. I hope you understand this. So this way, what we're going to get is, we're going to get V escape whole squared, minus and minus will be positive, so 2 times gm upon the radius of the planet. And then what we can do is, we can actually take square root on both sides, so this will be under root 2 gm upon r, and that's how you can find the escape velocity, that is the minimum velocity required to actually leave the gravitational field of a particular mass such as a planet. Okay, so just remember that this m represents the mass of the planet that you want to escape, and r is the radius of the planet. Now, so once we done, so let's just try to find escape velocity of an object that needs to leave Earth. Now let's see that. So let's write it in fact. So what is the escape velocity of Earth? And let's even calculate the escape velocity of Sun. So what is the escape velocity of Sun? Okay, so let's do this. Well, in fact, I have to give you some data here for Earth and Sun. Just remember that the mass of Earth is 6.0 times 10 raised to power 24 kilograms. The radius of Earth is 6.4 times 10 raised to power 6 meters. The mass of Sun is basically 2.0 times 10 raised to power 30, and the radius of Sun is 7.0 times 10 raised to power 8 meters. Alright, we have to find the escape velocity. You just put 2 times, value of g is 6.67 times 10 raised to power minus 11, multiplied by the mass of Earth, that is 6.0 times 10 raised to power 24, divided by the radius, which is 6.4 times 10 raised to power 6. Okay, so the answer you got is 1.12 times 10 raised to power 4 meters per second. Alright, if you look at the Sun, we have to do the same thing, and that would be basically escape 2 times 6.67 times 10 raised to minus 11, that's g. The mass of the Sun is 2.0 times 10 raised to power 30, and divided by 7.0 times 10 raised to power 8. Okay then, so what you told me was 6.2 times 10 raised to power 5. Okay, now interestingly, you see the escape velocity for Sun is lot more than the escape velocity of the Earth, because of the fact that of the nature of the mass. So the mass of the Earth is way smaller than the mass of Sun. But there's one thing very important to understand and see. What we are talking about is we have not considered the mass of the object that's being thrown. So basically, irrespective of the object, we need to understand that on Earth, if I throw myself out, okay, of this Earth, so I need to have this kind of velocity. Okay, so this is like for any mass, you need to have this velocity. Then why would you think that? Do you think throwing a tennis ball or throwing a car, which one will be easier? So basically, you need to understand why a greater mass or object would be harder to throw, because then you have to talk about momentum basically, and momentum tells you that basically it is mass and velocity. Even if you need to have you have an escape velocity achieved and there is a greater mass, so which means greater momentum is required. So something is at rest, so you need to actually bring it to, you have to change the momentum, and when you have to change the momentum, so basically you need to have a greater force applied. So that's why an object with a smaller mass is easier to throw at an escape velocity. However, this value for a particular planet or a particular star or a particular place would stay the same. Doesn't matter. So then you need to check the change in momentum when it comes to that. I hope everything is clear. If you have a question, please do ask.